Radix sort is a sorting algorithm well known for its linear time performance under certain conditions. More on that later. In practice, it is usually not implemented as an in-place algorithm, so we need a second array. Radix sort is not a comparison sort like quicksort or merge sort. Instead, elements have a radix, which is basically a number to sort by. The core idea of radix sort is to sort by each digit of the number sequentially by using a stable sorting algorithm. The ideal sorting algorithm for the digits is usually counting sort because it has linear time performance, but you could use any other stable sorting algorithm. In this example, I've used base 4 numbers. Instead of having digits from 0 to 9, you have 0 to 3. In practice, you'd use a larger base to have less digits, but I think using a smaller base captures the idea better here. Using a power of 2 base is more efficient, as we'll see in code soon. First, let's see the least significant digit first approach. In the outer function, we loop over all the digits. Now we run counting sort on the highlighted digit. First, we count how many of each digit there is. But how do we find the digits in base 4? Computers use binary, which is base 2. Base 4 digit will be 2 bits, base 8 3 bits, and so on. We can just extract the groups of bits as indicated by colors. We can mask the bits we don't need. For higher bits we need to shift first. In non-power of 2 bases you would have to use division and modulo operations. Getting the digit is done on lines 6 and 17. Now we reserve space for elements of each digit. We know we have a 10 of digit 0, so elements with digit 1 should start at index 10. We accumulate the counts left to right, and then shift one place right. Now we just move the elements to the other array based on digit. From here the process is repeated on the other digits, swapping arrays each time. We can't use the exact same algorithm for most significant digit first. Instead of running the counting sort on entire array every time, you have to use it on the sub-arrays after each iteration. Here's a recursive implementation. As you can see, we've made much more progress in one step. Now instead of running the counting sort on the entire array, we run it on the sub-array recursively. Performance could be improved a lot by using something like insertion sort for the smaller arrays. A lot of details could be changed here, but I hope it captures the core idea of the algorithm. In theory, Radix sort has linear time performance. The array elements in this video had maximal value of 256, which can be fit in 4 digits in base 4. We could have as many elements as we want, but we'd only have to go through the array 4 times. But what if each element had a unique value? Then we'd still have logarithmic time performance. Also, it not being a comparison sort makes it less flexible. It can outperform something like quicksort, but it isn't used as much.